Okay, so this is the Leaving Cert 2020 Maths Higher Level Paper 1. The exam was on today and I've just had a quick look through the paper. I'm just going to give my opinion on a couple of the questions. I'm not going to go through the solutions in this video. I'll do a solutions video for it hopefully in the next couple of weeks. But overall, I thought the paper was pretty fair. There was a few things in it that looked different than what you would be used to seeing, but that's the way of Leaving Cert Higher Level Maths. You need to be able to solve questions in both familiar and unfamiliar circumstances, and there was certainly a couple of unfamiliar circumstances in this paper. So let's have a look quickly through. So it started off with question 1, and that was a quadratic where the constant p is unknown and you have to find the value for p where x plus 3 is a factor. So sub in f of minus 3 and you'll be able to solve for p there. The next part does look a little bit trickier. Find the value of p for which f of x has roots which differ by 3. Now for this part, we can see that p is between minus 3 and 8. And if you think about how you would factorize a quadratic, you want your factors of your constant p to multiply, obviously, to give you p, but add to give you the coefficient of the x value. So we want a number between minus 3 and 8 that the factors of it add to give you 5. Well, the only one I can think of there is 4. So 4 is between minus 3 and 8. 4, we could choose factors of 4 and 1, and that would give you 5. So that could be, they differ by 3. So that could be the solution to that one there. Find the two values of p for which the graph of f of x will not cross the x-axis. So if it doesn't cross the x-axis, that means it doesn't have real roots. So that means if you did the discriminant b squared minus 4ac and let that less than 0, you should get two values, and obviously they'll be between minus 3 and 8. And then find the range of values of x for which 2x plus 5 minus 1 is less than or equal to 0. So this has no relation to the first bit, and it's just a modulus equation, so or a modulus inequality rather. So you need to deal with the modulus by squaring it out, and then it's just a quadratic inequality after that. On to question 2, our complex numbers question. Now this looks very different than anything you would have seen before. It's simultaneous equations with complex numbers. So from what I can see there, you're looking at doing some sort of substitution there with Z1 into this one, and see how it goes. I haven't worked through it, so I'm not sure how it'll work out as we go, but that should be what we're doing. You probably have to divide by the I to isolate Z1 and then sub in there. The complex numbers 3 plus 2i and 5 minus i, the first two terms of a geometric sequence. Find or the common ratio, so divide one by the other. Then use de Moivre's theorem to find the 9th term of the sequence. So if we want to find T9, that would be the first one times the common difference to the power of 9, perhaps. And then you're using de Moivre's theorem to do that. So that could be a tricky question. We'll see how it goes when I'm actually doing the solutions out next week. Question 3, then we've two functions, f of x and g of x. Investigate if the composite function f after g of x is equal to the composite function g after f of x. So just do one function followed by the other and then do them in reverse, see if you get the same answer. The real variables y and x are related by y is equal to 5x squared. The equation y equal to 5x squared can be rewritten in the form of this here. Find the value of a and b. So I'm thinking that perhaps we take the log base 5 of both sides, then work on this side to get it separated out like this, so you can separate it because it's going to be log base 5 of 5x squared. So that's the log of 5 base 5 and log of x squared base 5. Log of 5 base 5 is going to be your a. The log of x squared, you can bring the 2 down. So using your laws of logs there doesn't look too bad. So hence or otherwise, find the real values of y. So where this holds true, well, I'm thinking that we can probably, instead of the left-hand side, we can sub in this once we have our values of a and b, and then use our laws of logs to simplify it down and see what we get for x. So it could be tricky. You'd have to have a good knowledge of your logs for that one. Question 4 then, some more functions. So we have a function f of x and g of x. F of x is this cubic function here, and there's a coefficient k unknown in it there. Given that the first derivative at the point 3 is equal to minus 12, show that k is equal to minus 9. So you're going to have to differentiate this. You can differentiate it in terms of k there. You just, when you differentiate that bit, you just get 2kx. Sub in 3 into the derivative and let it equal to 12. You should get k is equal to minus 9. And that shouldn't be too bad. Part B, the function g of x, so that's the line function here, the linear function, is the line that passes through the turning points of the cubic function. Find the equation of g of x. Well, to do that, you're going to have to find your 2 turning points, and then you'll have 2 coordinates, and you can just use your equation of a line formula then. Show that the graph of g of x contains the point of inflection of f of x. So similar then, you'll have to find your point of inflection then of this cubic function, and then sub in your coordinates of the point into the equation of the line and see if it holds true, and it should. So not too bad a question there. Should be able to work through that one okay. Then we're on to question 5, financial maths. A couple agreed to take out a loan or a mortgage of 250,000. So we're asked to find the monthly repayment on the mortgage. So just your standard amortization there. Another couple agreed to take out a mortgage of 350,000 at a rate of 0.3 per month. Now this one's a bit trickier. So after 11 years, they're going to pay off the rest of the balance, and you're to get a series including the first 2 and the last 2 terms. So we have a repayment. You have to get the present value of this repayment for each of the remaining months over the 11-year period, and you have to write down the first and second. So you need to bear in mind that the payments are at the end of each month, so that's going to affect the present value of them, and then work out what the total value of that series is. So it could be tricky for some students there. If you know your sequences and series, then it shouldn't be too bad. Question 6, a differentiation from first principles question. So this one is fine. If you know how to do first principles, you should get it, no problem. If you don't know how to do first principles, then you won't be able to do it. So it's either you've learned it or not. Part B, you're given this function here, logarithmic function where c is a constant. Find the derivative. That's easy enough because it doesn't matter what c is. When you differentiate it, it'll be 0. So just differentiate this part here. Part 2, the diagram shows part of the function of the derivative of h of x. Here it is. The shaded region has an area of natural log of 3. Find the value of a. So we're given, this is the derivative. So if we integrate that, you get this here. So they're linked together, and we just need to use the definite integral between these 2 values. These will be our limits of integration, 0 and a. But we know the answer is log 3, so you can use that then to find a. On to section B then, a patterns question, numbers, triangular numbers, fill in your terms here, so you're just adding on the next natural number each time. Is this a triangle, or you're given the formula for a triangular number here, and is this a triangular number? Well, just put this in instead of Tn and solve for n. If n is a natural number, then it is. Then we have over here the n plus 1th triangular number can be written as this. Write the expression n by n plus 1 over 2 plus n plus 1 as a single fraction in its simplest form. So multiply this and divide it by 2 and write them as a single fraction. Prove that the sum of any two consecutive numbers, consecutive triangular numbers rather, will always be a square number. So for this, I'm thinking you need to get this here and this here and then add them, and your answer, you should be able to get it in the form of a square number. Whatever way that will work out, it'll be something squared, which means it's a square number. Two consecutive triangular numbers sum to 1,000 or 12,544. Find the smaller of these two numbers. So for this one, perhaps that's linking this one here. We can again have the sum of this plus this here. We can have it equal to that and solve for n. So we'll see what way that works out in the solutions as well. And here's something that a lot of students might not have seen before. So some numbers are both triangular and square. For example, 36. Euler in 1778 discovered the following formula for these numbers. This is Euler's formula, where nk is the kth term. So find n3. So you're just doing the n of 3 in that. So you should be able to do that, subbing in 3 instead of k. Then we have over here a proof by induction, which is great. If you know how to do your proof by induction, you should fly through that one. Question 8. Then a rectangle is inscribed in a circle like this. And we have this angle here, it's radius 5. The point or can be written as a cos theta, b sine theta. If you know your unit circle, you should be familiar with that. So just you're looking for the length of this side and the length of this side in terms of theta and 5, and it'll be sine and cosine as well. So you're using your trigonometric formulas to find that. Show that the area of the triangle measured in square units can be written as this. So perhaps using your area formula on this, half AB sine C, it'll work out to give you that. Use calculus to show that the rectangle with maximum area is a square. If you've done much calculus, you should know that already, that the maximum area of any rectangle is when it's a square. So we are probably going to differentiate this and find the maximum value of it, and it should work out that it's a square. Find this maximum area then. A couple of ways you can do that. You could just go and let this be, this radius is always going to be 5, let this equal to this, solve for the sides, and then find the area. So that should be okay as well. On to the next bit, part B of this one. A person who is 2 meters tall is walking towards a street light of height 5 meters at a speed of 1.5 meters per second. Find a rate in meters per second at which the length of the person's shadow cast by the street light is changing. So rates of change question there. Okay, so hopefully that one's all right. And again, we'll have a look at the solution next week. Question 9 was a nice logs question. Looked very familiar, this one actually. Find a number, this is your function, find a number after 4.5 hours, just replace t. Find a time in hours that it takes the bacteria to grow to this, so you're letting 790 over here, find t. Then we have the average number of the bacteria between t equal to 3 and t equal to 12, so that's your average value of a function formula, which you have and you should have used before, so you should be able to do that one. Find a rate at which it's changing when t is equal to 12. So that would be find a slope when t is equal to 12. That'll give you the rate it's changing at. So differentiate and let t equal to 12. After k hours, the rate of increase is greater than 90 bacteria per hour. Find the least value of k. So for this one, we differentiate and then we're looking for t, or k is replaced by t, but we just let the derivative greater than 90 and see what values we get there for that. And then the last bit, the number of bacteria in the early stage of a different colony can be found using this function. We want to find when they'll be equal, so let this function equal to this function and solve for t. So that was the paper. Now, I haven't tried any of the questions yet, so they were just my first initial thoughts on all of the questions. So perhaps some of them will be done slightly differently to how I first looked at them, and that's fine. We'll have a look at doing the solutions video over the next week or two, and I'll do the same with paper 2. I'll have a look at it later on today and see how that looks, and then do a solutions video for that one as well. So if you have any questions about it, let me know in the comments below. What did you think of the paper? Do you think it's a fair paper? Whatever comments you have, let me know. And thanks for watching, and I'll see you in the next video.